Welcome to the second part of this journey into model predictive control in MATLAB. And today we're going to look at constraints on the manipulated variable. So let's start from here. This is the first slide, the presentation, which is similar to what you have already seen. So today we recap what we have seen last time, and then we will analyze constraints and how to set them up and the effect on the response of the control system. Okay, so it's very important, remember the address of the repository. This is public, so you can find the code, exactly the code that I'm showing today. Okay, just a quick recap of the cost function. I'm not going to go into this mathematically again, but remember that this is an optimization, so a minimization in this case of this cost function constrained. Okay, so a very important feature of model predictive control is constraints and how constraints are handled in a multi-input, multi-output system or single input, single output, but it's a very important feature. So this minimization is always subject to constraints. And how we set the constraints is how we can reap most of the benefit of the algorithm. The plant, you probably remember it from the last video, is an object, a box that is sliding on a surface with linear friction, coefficient is k, is pushed by a force F, which is our control variable. And we can find the differential equation of the motion here. So it's very simple. It's something that you have surely already seen. This is obviously the interest here is not to control a complex system, is to show the functionality and the features of this control algorithm and how to implement it in MATLAB. State space model, as we said before, we have to put the system into state space for the control algorithm to function and for us to be able to set it up. And this is how it comes out. We have already seen this, so I'm not going to talk too much about this. Okay. Again, same for this. This is the architecture, relatively simple, already seen. Remember that in MATLAB, for the linear model predictive control, which is what we're doing now, we get for free a Kalman filter in the implementation, because we always need a state estimator with model predictive control, unless we measure all the state, which is possible in our simple examples, but is probably unlikely in reality. Okay, so if you have to implement this on a real system, very likely you will not have all the state and you will need a state estimator. In MATLAB, you get the Kalman filter for free for the linear model predictive control. For the non-linear, we have to implement the Kalman filter separately, but that's a different story. In this case, we have it integrated. And then this is the algorithm, set point that goes to the algorithm, which will generate the control input, which will go and push the object and move the object. Then we measure the position, and this is important because of what we said. The position is the only thing that we measure, but the state has, if we go back, the state has also the speed of the object, which we don't measure, but we estimated internally in the algorithm via the Kalman filter. Okay, now instead of looking at the code here, we will look at the code in MATLAB, because I think it's more interesting. So this is how you see the repository, exactly the same way as you will see it if you go on the address that I've showed you. Now, if we remember, we have the first section where we set the parameters, which we still need. Then we have this section where we define A, B, C, D for the state space model, and we use the ss command to create the state space model. So we will run this as well. Now we need to create the MPC object, okay? And this is the same we've done last time in the previous video. Remember, we start with a constraint on the manipulated variable, which is minus 10 to plus 10 Newton, because this is a force. We have our scale factor for the calculation of the cost function. Then we set also a constraint on the output variable, but this is basically outside of reach, so it doesn't really do anything. Our set point will be 1, so that this is irrelevant for now. We will have a video on this in the next weeks. And then we set the weights. So 1 on the output variable and 0.1 on the rate of change. No weight on the manipulated variable. This is because it depends, but we will discuss it in more detail. But essentially, if you want the manipulated variable to go back, or to preferably go to a certain value once the set point has been reached, you may want to put a weight here. But that might create steady-state error in presence of certain disturbances. So essentially, if you don't need it, generally I prefer not to have a weight on the manipulated variable. Manipulated variable rate of change instead is very important because it decides how smooth or how aggressive your algorithm is. So higher weight, smoother algorithm, smoother control, probably slower, generally more robust. Smaller weight, you get a more aggressive algorithm, probably less robust. Okay, so we set this up using the MPC command. We have our sample time, which is 0.1 in this case, 0.1 seconds. We have 10 prediction horizon, 2 control horizon, and then the weights that we have just set, and manipulated variables and output variables. Okay, so we run this. Done. Now we skip this section because it's what we did last time. This will plot the result as it is. Now we want to do something slightly different, which is a comparison between different constraints and see the response with different constraints. And I think this is interesting because it's something that I do a lot when I code with MATLAB, and when I want to simulate the same thing many times with slight variations, and then plot everything on the same plot to see the differences. This is a simple approach that I took. Sometimes I use a structure, but in this case I've just used a matrix. Okay, so the simulation time is 6 seconds. Then we calculate the steps, same as before. We give it as a reference signal, a set point that is 1. Then we set this matrix of constraints, which is essentially each row has max and min for 3 different scenarios. Then I set the colors that I want for each of the different scenarios. Then I set the labels that I want in the legend. Then initialize the cell arrays to store the results for each scenario. Okay. Right. So we take the length of the constraints matrix. Then we generally use this approach. I clone the original MPC object because I don't want to pollute it for later simulations. So sometimes I have a long list of simulations here and I want to start fresh every time. So I copy this, then I change the constraints on the manipulated variable. Okay, max is set to basically these or these or these depending on the index, and then I do the same for the minimum. Then I run the simulation, exactly the same approach as we've done before, and then we plot. Plotting is also interesting, I think, in this case. Okay, forget all the colors. I mean, don't forget it. If you're interested, have a look at it, but I'm not going to walk you through it. But for how to plot each response, I'm using a for, and I'm holding the previous plot essentially. Okay, so I enable hold on, then I cycle through the constraints, and I use the cell arrays that I initialize here, the appropriate one every time. And I plot it in this case 3 times. Then we plot the set point, which I plot from the first run. Okay, I take the time from the first run because it's always the same. And then I disable hold on, and I have the legend, which again is interesting because it's using labels which I've defined here. So it's a bit of a slightly automated approach to plotting and running different scenarios. Second plot is basically the same, but you don't have the set point because I have only the control effort here, the fors in this case. So I have just the for loop. Okay, let's see what we get. Okay. Okay, so you can see that as expected, I think, our response is slightly worse as we have stricter constraints, right? So the less we can play around and the less force we have available, the less control authority we have available, we will have a slightly worse response because we have less authority. And we can see this, right, with the green, which is plus minus 20, we get a faster response, and then we settle. The overshoot is probably slightly worse than the second response, but overall the cost function is minimized much faster because we get to the set point faster. Then for the plus minus 10, which you can see here, the control effort, we get a slightly slower response, similar overshoot, maybe slightly better, but slower response. And then for the plus minus 5, as we expect, we get the magenta, we get an even slower response and quite a bit more of overshoot. Okay, so this is the best it could do with this control authority. I think everything is as expected. I always like to see how MPC handles constraints because it's different from other controllers like a PID with simple saturation. Here you see that it knows where it has to go straight away, right? There's no ramp here. It goes straight to 20 because that's the maximum it knows it needs to do. And then it will, in the case of 20, it doesn't need to saturate it to minus 20, but for example, in the case of 10, it goes from plus 10 to minus 10. Okay, I hope you enjoyed the video. Thank you for watching. I'll see you in the next one.